Alright, let's begin this video with the challenge problem from the last video. So we are looking for a relationship between the acceleration of these two satellites. Well, we know that their acceleration is going to be centripetal. And we know that centripetal acceleration has a centripetal force related to it that is due to the force of the gravity from the planet. So we can write that centripetal acceleration is due to gravity, which is related by our gravitational constant times the mass of the planet times the mass of the satellite divided by the radius of orbit squared. And that radius squared is the key relationship to solving this problem. So we know that our a sub y will be all of the numerator divided by 2r sub x squared. So you square each individual term. And we know our acceleration on the x satellite also have the same numerator divided by r sub x squared. So what we can do is take the ratio by dividing both of these. We can see our numerators cancel out, and we'll be left with a sub y divided by a sub x equals r sub x squared divided by 4r sub x squared. So the radius of our x satellite cancels out, and if you solve for a sub y, you will get a sub x divided by 4. So that makes B the correct answer. In this video, we are going to be studying energy, and in AP Physics 1, there are 3 types of energy you need to be familiar with. The first one is kinetic energy. This has to do with motion. Any object in motion has kinetic energy. The formula for this is K, E, sometimes you might see a K, equals 1/2 of the product of the mass of the object and its velocity squared. So for example, if you double the mass, the object will have twice as much kinetic energy. If you double its velocity / its speed, because the velocity is squared here, then you quadruple the kinetic energy. And another thing to note is that because our velocity is squared, kinetic energy is always a positive value. The second type of energy you need to be familiar with is gravitational potential energy. I'm going to denote that as GPE. This has to do with an object's ability to fall, or its height. And the interesting thing about gravitational potential energy is that unless otherwise specified, you decide the 0 point. And you should always pick this 0 point or the 0 line at a point convenient and easy to do the calculation. This you might see denoted as PE or U sub G equals the product of an object's mass times the gravitational field times its height above the 0 line. And typically that 0 line should be pretty obvious as to where you should put it. And the third type of energy we are going to be looking at is going to be elastic potential energy. This potential energy has to do with springs. So springs is a new topic to us. We will study it much more extensively when we get to simple harmonic motion. But to give you an idea of what we mean when we speak about elastic potential energy, think about having a horizontal surface, and that's not the best spring. Think about having a spring here, and this is its natural length. Now imagine that you compress it to some length here, and some length even lower than that. The further that you compress that spring, the larger the force within the spring is going to get, because it wants to restore itself back to its natural length. Alright, so the equation for that, you might see it denoted as U sub E is going to be 1/2 kx squared, where k is the spring constant. The spring constant tells you how stretchy a spring is, or you can say how resistant it is going to be to a change in its length. And x is going to be the displacement from equilibrium. So say you have a spring against a wall. This is its natural length, and you extend it a distance here to that second dashed line. This will be x. Now note, x is not the length of the spring, it's the distance that you stretch it from its natural length. So do not get those two values mixed up. Alright, another thing we need to talk about is the law of conservation of energy, and this is a critical law. This is one of the more foundational ideas of AP Physics 1 that you really need to be fluent with. So the law of conservation of energy states that the sum of the initial energies of a system, where a system is the collection of objects that you are defining, is going to be equal to the sum of the final energies in that system. So say, for example, that we have our energies, kinetic energy initial, plus our initial gravitational potential energy, plus our initial elastic energy is going to be equal to our final kinetic energy plus our final gravitational potential energy plus our final elastic potential energy. Now, oftentimes you won't be using all three of these energies. You might only have two of them. So in that case, you don't have to worry about the third type of energy. But know that the sum of these energies has to be the same, and this is a very useful equation that you can use in a variety of problems that we are now going to look at. I should make a quick little side note that we will study more later once we get to work. This law is assuming that there are no outside forces acting on our system. For example, say you have a block of wood and you have an object sliding across it. It has some kinetic energy. We're going to set our gravitational potential energy to be 0 at the surface. And that's what I mean when usually your zero line will be pretty obvious. It has some kinetic energy here. Eventually it reaches here and it has 0 kinetic energy. You might say, didn't that violate the law of conservation of energy? It had kinetic energy. That was the only energy it had because we have 0 gravitational potential energy and we're not dealing with springs. But there is friction here. Friction is an outside force. It is doing work. That is something we will study later. But all of that kinetic energy went to heat from friction. So you could say it went to thermal energy, a different type of energy that you will study in AP Physics 2, but not here. But just keep that in mind, that when you're using this law, you need to make sure that you have no outside forces acting on your system, and we will learn how to deal with those outside forces in a future lesson. Right, here's a little bit of a fun problem to start us off. It's really more of a kinematics problem. However, one of the answer choices does have to do with energy, so it's a good introduction to working with energy problems. So we've got a rock of mass m dropped from a tall building. Half a second later, a rock of 2m, so twice the mass, is dropped from the same height. We're saying air resistance is negligible, so which of the following would be true? Alright, let's look at option D because we are focusing on energy. So we know our potential energy, right? Because we're not dealing with springs, we're going to have no elastic potential energy here, and we're dealing with falling. They're in motion, so we've got kinetic energy, but they're dropped. So we start off with some gravitational potential energy, and we know that UG equals mgh, right? And using our conservation of energy, the only initial energy we have is going to be UG, and let's let 0 equal the ground for our potential energy. So then when they land, they've only got kinetic energy. Right? Now, the first rock is of mass m, the second rock is of 2m. So our second rock has twice the initial potential energy of the first. So we're going to say UG2 equals twice that of UG1. That means when they hit the ground, KE2 is going to equal twice that of KE1. So they are not going to hit the ground with the same kinetic energy. If we're saying air resistance is negligible, the second rock will have twice the kinetic energy of the first rock. So D is not a plausible answer. Now what I want you to do is look at option B. Right, I want you to make a kinematics chart with our variables and see if D is a plausible answer. Just a moment while I get rid of all of this writing. Alright, so we know that both rocks have an initial velocity of 0. We do not know the final velocity. We know they have an acceleration due to gravity. We know they have the same change in y, and we're looking for a change in t. So we want an equation with no final velocity. Hopefully you know which one that is. Change in y equals our initial velocity times time plus 1/2 our acceleration times our time squared. Initial velocity is 0. And in that equation we see nothing to do with mass. Our other variables are the same. So if the rocks are dropped half a second apart, they will hit the ground exactly half a second apart if air resistance is negligible. So B is claiming that not to be true, so it is wrong. And hopefully you will say that C is also wrong because that acceleration is due to gravity. They're in the same gravitational field. Acceleration will be the same as due to G, right there. That means A is the correct answer for this problem. Alright, so in this problem we have a block oscillating without friction on the end of a spring, and we are given its maximum and minimum lengths. So we want to know which graph would represent the total mechanical energy of the system. Right, so the first thing we need to think is, are there any external forces acting on the system? And because we are without friction, the answer would be no. So because of that, we have to abide by the law of conservation of energy, which says that the total mechanical energy is constant, and thus option D is the answer. For the final part of this video, we want to know which graph could represent the kinetic energy of the block as a function of its position. Alright, we will study this extensively when we get to simple harmonic motion, but for now, you need to remember that the sum of our elastic potential energy plus our kinetic energy is going to equal a constant value. The next thing I want you to think of is when you release that block, you are going to release it from rest. And when you release it from rest, it's going to be at its minimum or maximum position depending on whether you stretch it and or like pull it out. Right, because you'll either release it here or here, so you'll either push it into its minimum position or pull it out to its maximum position. And at that point, it will be at rest. And here, for our 1/2 kx squared, that x will be at its maximum value. Our kinetic energy will be at 0. So therefore, at our minimum and maximum positions, we have to have 0 kinetic energy. The next thing I want you to think of is when we are in between those two positions. Because right in the middle here is our equilibrium position. And at that point, our stretch from equilibrium is 0, so that block is going to have all kinetic energy at its center. So that means between x min and x max, we have to be at our maximum for kinetic energy because we have no elastic potential energy. So we can rule out A and D, leaving us with B and C. And we know kinetic energy is 1/2 mv squared. V is parabolic because it's squared, so C is the answer. Alright, I know that last part was a bit much. It was a lot of new information, so let's just make ourselves a chart. This will be x min and x max, and this will be for equilibrium. This is going to be our UE, this is going to be our KE, and here's just a little drawing. Alright, EQ stands for equilibrium. Alright, so at x min or x max, our spring or block is being released from rest. So here we are going to have 0 kinetic energy. And at that point, 1/2 kx squared, x is going to be at its maximum. So we are going to have maximum elastic potential energy. Now at equilibrium, we have 0 stretch from equilibrium, so therefore we have 0 elastic potential energy. And because Ke plus U sub E has to equal a constant, if this is 0, then this has to be at a maximum. So we have the maximum kinetic energy and thus the maximum speed when we are moving through equilibrium. So you need to know this chart, and we will definitely come back to it later. But if you were feeling a little overwhelmed by the last problem, just think through the equation right here. You can get all of this from knowing that Ke plus Ue has to be a constant. Here's the challenge problem for this video, and I know it is a challenge, especially and mainly because this is the first video on this topic. So I'm going to give you a little bit of a hint, and that is going to be knowing that Ke plus our elastic potential energy is always a constant, the sum of them. However, our Ke max has to equal our maximum elastic potential energy, right? Because if our elastic potential energy is 0 here, then Ke equals the constant, and if Ke is 0, then U sub E equals the constant. So at their maximum values, kinetic energy and elastic potential energy are the same. So use this and see if you can derive an equation for the force or spring constant, which, if you need a reminder, is K. So the solution will be on my Instagram page shortly after the release of this video, or you can find it at the beginning of the next video.